Okay, let's continue and explore some few more questions about the scale of the universe. For example, we're gonna look into wondering how big is Earth compared to our solar system, how far away are the stars, and how big is the Milky Way galaxy, the universe, and also we're going to try to answer the questions to how does our lifetime compare to the age of the universe. So let's start with that. How big do you think is Earth compared to the solar system? Well, now, in order to do that, I think we should find it very useful to reduce the size of basically everything, but we're going to stop at the size of the solar system. We're going to reduce it by a factor of 10 billion. Again, very useful to work with scientific notations. So 10 billion is 10 times the definition of a billion, which is 10 to the 9. So we have a ratio of 10 to the 10. All right. Okay, well, let's see how big the sun would look like on that scale. Well, first of all, size of the sun, say the radius of the sun, now we know, is about 700,000 kilometers. But I'm going to write it in scientific notation, and that's going to be 7 times 10 to, how many zeros we have? 1, 2, 3, 4, 5. 5 kilometers. All right. Might be useful to actually write it in meters as well, right? So 1 kilometer, that is times 10 to the 3 meters. So the whole radius of the sun is going to be 7 times 10 to the 5 plus 3 meter, or 7 times 10 to the 8 meter. On 10 to the 10 scale, so reduced by a factor of 10 to the 10, the radius of the sun would be 7 times 10 to the 8 meter divided by 10 to the 10. Remember the division of the powers of 10, we're going to have 7 times 10 to 8 minus 10 meter. That's 7 times 10 to the minus 2 meter, or 7 or 0.007 meter. That is 7 centimeter. All right. Does this make any sense? How does this compare with what's written here? What do we have? It says here the sun on that scale looks like is 14 centimeter in diameter, where it does make a lot of sense because the diameter is 2 times the radius, so we're gonna end up with 14 centimeter, exactly how it says there. Okay, so now on this scale, how big do you think the Earth is? And I'll tell you also how far away from the sun that is. So you can continue with very similar calculations like the ones we've done for the radius of the sun. So we're gonna do it for the Earth now. Okay, so radius of the Earth, you can look it up, Google can tell you that is about 6,400 kilometers. So now we're gonna scale it to 10 to the 10, right, which is 10 billion. So what do we get? Again, try to work with scientific notation because it's just so much easier to manipulate the powers of 10. So we have 6.4 times 10 to the 3. So this was this number. And then we have the kilometer, and we're going to write it in meters because we're going to need something really small. So again, this is 1,000 meters, or 10 to the 3 meters divided by 10 to the 10. 10 to the 3 times 10 to the 3. These together make a 10 to the 6. All right. And so that means what we have here is going to be 6.4 times 10 to the 6 minus 10 meter. We're going to continue. This is 6.4 times 10 to the minus 4 meter. We know we can use it. We need a different unit just to make a bit more sense of this, remember that 1 meter has 1,000 millimeters, or 10 to the 3 millimeters. So we're going to use that. So you have 6.4 times 10 to the minus 4 times 10 to the 3 millimeters. These two together, they're going to be 10 to the minus 4 plus 3, so 10 to the minus 1. 10 to the minus 1, we're going to multiply it with 6.4, so about 0.64 millimeter. Woo! What do you think the correct answer to this question is? Like, how big is the Earth on a scale of 1 to 10 billion? Would it be an atom? Would it be a ballpoint? A marble? A marble, I think, is a lot larger than 0.6 millimeters. Also, the golf ball, so no. The atom is actually much smaller. This is 10 to the minus 10 meters. So again, not a good match with what we got in our calculations for the radius of the Earth. So the correct answer is the ballpoint. Okay, so you have in Mastering Astronomy an applet that is introducing you to the voyage scale. Okay, the voyage is the name of the model solar system that's using this scale on the National Mall in Washington, D.C. You probably recognize the name of the street, Jefferson Avenue, that is right in front of the National Air and Space Museum. Just if you're just in front, on that street in front of this museum, you're going to realize there's some signpost for the sun, and then you're going to have to, so imagine you have a grapefruit there, right, for the sun, as large as a grapefruit. Okay, so something in size, like maybe a softball as well. And then you need to travel to the next planet. Somewhere here will be Mercury. And then you travel some more, you're going to find Venus. And then by the time you travel about 15 meters away from the sun, you are going to find the Earth. And then you keep going, just to give you a sense of how far away the planets are from one another. Actually, that's pretty inaccurate because the planets are not aligned like this. That only happens every once in a while, very rarely actually, right? They do rotate around the sun. So this is basically how big the radius, right, of this, the orbit of Jupiter is relative to the sun, right? And then you have the radius of the orbit of Saturn, and so on, right? So these are radii, and the planets are, just anywhere on these orbits. Okay, but anyway, it's pretty cool, right? And I think the major lesson that you're going to learn from this, whether you're just playing with the applet or just have the chance to walk on that Jefferson Avenue and just walk basically in between the planets, the major lesson is that the solar system is almost entirely made of nearly empty space. Okay, another thing, you probably now wonder how far away the stars are, and again, would that be enough to have a 1 to 10 billion scale? Right? Well, on that scale, it's going to be a few minutes to walk to Pluto, right, from the sun. But how far away would you have to walk to reach Alpha Centauri, which is the closest star to the sun, that is closest star to our own solar system, and also the closest star to us as a planet. So some options here would be 1 mile, maybe 10 miles, 100 miles, or as it turns out, you will have to walk on that scale 1 to 10 billion. You would have to basically walk the distance across the United States, so about 2,500 miles. So again, the lesson learned is that there's a lot of emptiness out there, right? So if the closest star to us, right, us being a grapefruit-sized sun and the planets around it in Washington D.C., then this closest similar system that exists up there is in San Francisco, right? Okay, so again, follow this applet and you can zoom out or in just to play and with just figuring out the scale of things. Now, on this same 1 to 10 billion scale, what do you think? How big is the Milky Way? It's going to be huge. You're going to have to zoom out a few times. A few times, that is times 10, times 10, times 10. Okay, so a few orders of magnitude. This is what people mean by the order of magnitude. It's the factor of 10. Larger and larger and larger and larger. Hey, so I told you, and we as astronomers, we figured it out that there are actually about hundreds of billions of stars in one galaxy. And that's definitely true for our own galaxy. Okay, so suppose you try to count 100 billion stars at a rate of 1 per second. How long would it take you? What do you think? Just again, another way of thinking about the vast number of stars that exist in our own galaxy. And then if I tell you that there are about 100 billion galaxies in the universe. How many total stars? Total number of stars? Well, that is going to be number of stars per one galaxy times these 100 billion, right? So this is 100 times 10 to the 9, okay? So again, this is 10 to the 2, so the whole thing is 10 to 11. All right, so what do we get? What's again the number of stars in one galaxy? This is 100 billion. We just calculated here. It's 10 to 11. So what do we have here? 10 to the 11 times 10 to the 11. So this is the total number of stars, which again can be written as 10 to 11 plus 11, 22 stars. You see, again, the usefulness of using the powers of 10. That's 1 followed by 22 zeros. It doesn't make any sense to use that kind of notation and just carry with you all those zeros. All right. Okay, so hey, let's count. Right, so what do you think? Can you do it 1 per second, first of all? And also, just a simple calculation. So you can try to work that out. So we have 100 times to the 9 stars, that is seconds, right? And you can convert that into maybe minutes, right? So you're gonna have, so this is again 10 to the 11, so 10 to the 11, and you can right, convert the seconds. You're gonna have to divide by 60 to get the minutes, maybe divide by 24 to get the hours, and then divide by, say, 365 to get days. So this would be 1 year, right? Okay, so how many years? I think it's nearly 3,200 years, right? You can do all that calculations. So even if you count, right, one star per second, right, you're gonna need, for 100 billion stars, you're gonna need 100 billion seconds, which is this many years, right? So if you are able to count one star per second, you would need a few thousand years. But can you actually? Can you really say what's coming after the number, say, 54,537,691? Like in a second, just how fast can you say that number and even remember what comes next? So anyway, if you think of it, the rules, if you want to count to 100 billion, definitely start soon, limit your breaks, and most importantly, don't die, right? Or stay alive for at least 300 and more years, right? All right, so that's just counting the stars. And guess what? We, as human beings, we became so ingenious that not only we were able to find out how many are there, we even gave names to them, we study them, we know which ones have planets, or at least some of them. We understand their properties, like, what's their colors, their temperatures, the sizes. It's an amazing world out there. All right, so this is supposed to be 10 to the 22, right? So just how big is this universe? Wow. This again is 10 to the 11, and this is 10 to the 11. We just did this calculation a minute ago. So in case you wonder, there are as many stars in this universe as grains of dry sand on all of the Earth's beaches. That's pretty amazing, isn't it? All right. One more thing to discuss in this mini lecture. How old do you think the Earth is? Okay. Some circulate the idea that the Earth is just a few thousand years old. You might have heard about millions or billions or trillions or whatever, right? How do we know? So the answer is this one. You can come back to it. So of course, it's about 5 billion, but it's definitely not 1, not 14 billion, and not 1 million, and much, much older than 6,000 years. We do have a lot of evidence for the fact that the age of the universe, as we know it, is 14 billion years, right? So again, that is 14 times 10 to the 9 years. Now, this is a really nice way to present the scale of time. It's a modified version of Carl Sagan's cosmic calendar. So here's what he thought about. It was like, why don't we put this duration of 14 billion years into one Earth year, calendar year, right? So that means basically one cosmic month would be the equivalent of 14 times 10 to the 9 years divided by 12, right? So that is around 1.2 times 10 to the 9 years. By the way, 10 to the 9 years, 10 to the 9 is giga, right? Giga year, if you want. Some people say that. Okay, so about 1.2 giga year per month. So each month, like if you put the whole age of the universe and history of the universe into one calendar year, so you're gonna start with the Big Bang on January 1st, and today is going to be December 31st, so today. Okay, so during its life, right, what we realized that when the galaxies like our own, just very first galaxies formed, was about 1 month into the age of the universe. So it basically took about 1 gigayear for galaxies to form, and it also took, 1/3 and another third of the history of the universe in order to have planets like Earth form. Okay, it took, and you can calculate the weeks. You can say divide by 4 to find the equivalent of 1 cosmic week, thinking that there are about 4 weeks in 1 month, right? So it took about basically 3/4 of a gigayear for the life to show up, to form on the Earth. And then so basically what I wanted to point out, right, if the whole universe is 14 billion years old and the Earth only formed about 2/3, right, so this would be 1/3 and another third, right, that means, right, about 14 billion years divide by 3, so around 5 billion years is how old the Earth is. Of course, on that scale, there are some really nice things to notice. Life as we know it actually happened basically during the last month, and not even, it's probably so the dinosaurs died just after Christmas, and then actually life as we know it, right, happened in the last minute of the universe, right? Which it's pretty cool to think about. All right, that's it.